I'm going to be talking about antenna. All of my talks about antennas and fields. And I know this conference is not heavily on antennas, but the talk I give it in more antenna propagation conference. So I'll try to give you an idea of what is it really I'm going to be talking about here in a bit of a less analytical and less complex way. What does the title suggest? That we're actually looking at the near field and looking at new applications, antennas, and so on. So I'll summarize to you. I believe the electromagnetic community and electromagnetic research is at a crossroads now. We've been doing research for the last 50, 60 years, and as you're going to see, I'm going to give a bit of a history of research, but we have emerging applications coming towards us, and there are some very basic questions that we have not been able to deal with. And a good example is the near field of an antenna. We all know a far field, and we measure the far field and so on, but when we come close to the antenna itself, it's a mystery. And this is a bit of an odd situation because antennas are coming close together, applications, MIMOs, and so on, and it is really in the near field where most of the action happens, and this is what decides the antenna configuration, the antenna, how they work out. The same thing, antenna characteristic itself. We kind of use numerical method, use things, but we really don't have a feel of the analytical properties of the antenna. So what we asked ourselves this question 4 or 5 years ago, and as you can see, there are new applications come, electronic phone cap structures, metamaterials, near field communication, all of these things. And we seem to get into an area, and then we hit some roadblocks in terms of the approximations and so that we make. Numerical methods have some limitations when you have large arrays and so on. Also, in numerical methods, you assume pores or plane wave excitation and so on. But things happen in the near field sometimes. So what we did here, and what I'm going to give you a bit of idea out here, is the following. We actually going back to the fundamentals, and I really mean the fundamentals here. We look back at what has been done in the past, and we proposing a new description of the near field of any antenna, any generic antenna. So we have actually an analytical description of the field. This is generic. So the theory, we established that, but we have not applied it to too many antennas. So that in itself actually opens a new area of research for people who want to look at that. Now you have an antenna, and you know the near field of antenna, so can you relate it to the current antenna? So that led us to the interaction between two antennas. So what we're doing here, we actually have a new model for the antenna itself. And the model we have for any antenna is actually in terms of something like transfer functions. Antenna engineers like to use transfer functions. So we have a model where we can actually have a transfer function for the antenna. And based on these two things, and based on some simplification, we can actually do certain things and answer some of the new questions that are arising towards us. It's not easy. This is research in progress, but we actually applied it to some problems, and I'll give you some examples, a couple of examples. And it is work in progress, as I say. So we hope that this would make would reduce or direct things toward some new directions in research. Before I do that, just to give you some idea where I came from. I come from the Royal Military College of Canada. This is the main college for the Canadian military, for all the air forces and so on. Well, as you know, Canada is a big country, talking about 6,000 kilometers from far to left with 34 million people. So it's barely related. Kingston, that's where I come, right at the bottom there on the US border. It's the old capital of Canada from 1844. It's close to Montreal and Toronto and the center of population there. This is the military college right on the lake. This is Lake Ontario on the other side. And you can see the military college here, Queen's University, is very close by. So this is why I work at both places. Well, this is a very nice looking picture, and the place is very looking nice, but anybody who came to Canada would know that I'm lying here. because this is how it was when I left it. Okay, and I thank the committee here for making nice weather. I appreciate the few days I'm staying here. And this is basically the weather you can see in December. So until March, May, this is how we live in there. It is a historic place, the Royal Military College. It's actually 7 years after Canada became a country in 1867. The Royal Military College was formed. And it is a national institution, and you can see these two photos here. This is actually the original flag of the military college. And instead of the coat the arms here, they actually, Canada, when they were looking for a flag in 1964, they adopted one professor, John Matheson from RMC. He's actually the one that designed the Canadian flag. So the next February, they're going to celebrate 50 years of Canadian flag, which goes back to RMC. I just talked about the description of the talk here. And as I said, we'll introduce new fundamentals of electromagnetics, introduce something about the near field structure and the characterization of antenna. And at the bottom here, you see, we're hoping that doing a bit of the theory would lead us actually to new consideration in terms of numerical and also in terms of experimentation. I am quoting here Constantine Balanas, who gave a talk a few weeks ago. And this is what I refer to. Those of us who have been working in this area for many years, like myself, I've been working in the area for 40 years. The early days, there were analytical methods. So any problem, you had to have a boundary value problem solution to it. Well, not too many problems were there. Then came geometrical theory of diffraction by Joseph Keller in the 50s, and then 60s, so method of moment, numerical methods, and then commercial softwares, and very little done on the fundamentals. We never go back on the fundamentals. So this is what, so now this is a current research project that I just take you back to RMC here for a second. We do quite a bit of research in various areas like everybody else. Some of it is delegated to us from the military, but quite a number of it are in basic research and so on. And the one that I'm talking about is the second one there. The first three, I give DL talks about them, but I'm focusing today on the second one. I think Dr. Saudi Riyad introduced this a bit. How is electromagnetics related to what we have been doing since years? So go back to, this is all electromagnetics. In the 70s, communication satellites. Life is getting more interesting, many applications. And radars and so on, and getting complex. And again, you can see here antennas are an important aspect for radars. They are any radar without an antenna obviously is a blind, deaf thing. You see how many antennas could be there. If you look at a plane, nobody realized this, but these are the kind of, this is an old plane. This is a 20 years old plane, and you can see the number of antennas on there. And those antennas cover frequency range from kilohertz to gigahertz. All of these antennas coexist on the same body. So it is really important that we know how they interact together and so on. So it basically goes back to the one antenna. Do I know what's happening with the one antenna? Again, I thank the APS Society, IEEE, and here are, as again, I say the objectives of my talk. And this is basically a map of the talk. So what I'm going to do here, I'm going to talk about near field theory and what that near field theory leads to a new formulation, re-examination of energy concepts. Like we really know very little about the energy around the antenna, where the energy is stored in the field. We do circuit model of the antenna. But the circuit model is not really representative of what happens in the antenna if the fields change. The antenna, we look at it more as actually a field oscillator. So we develop new concepts here and look at the far field and whether you want to do metamaterial or anything else, it all would have to fit in here. So having known one antenna, then you get to the analysis of interaction between antennas. And here I will focus on two things: a new model, infinitesimal dipole model, and I'll show you example doing that. And then the new concept that I talk about is called antenna current Green function. This is a very new concept, and I'll just explain in general without going into too much details what it is. So this is a bird's eye view about the talk I'm giving here. So the green boxes here basically give the new development. So near field theory, antenna current Green function formulation, dipole model. And you can see the interaction or connectivity with this to the application. So if you're talking about energy, you actually need to use these two models. If you're talking about near field focusing, when I say near field focusing here, you want to have a certain radiation pattern. So how you design the near field of the antenna to get that radiation pattern. Near field metamaterial. Most of the work done in metamaterial is temporal. We're looking at a spatial variation of the energy around and so on. Mutual coupling. It's not a circuit concept. We're looking here at the field concept. MIMO systems, and I'll give an example how these developments are used in a MIMO system to achieve certain requirements. Energy. There are many questions that are being raised about energy. Where is the energy in the system, and the definition of reactive energy and the stored energy. And there are actually some contradictions if anybody does fundamental research on the question of energy in the electric fields and so on. The new formulation that we have, we're coming actually is a concept called localized energy and stored energy. Depending on the type of the antenna, the energy around the antenna actually could be localized in certain directions. Okay, and that depends on the antenna configuration and so on. Mutual coupling, the same thing. This is an important consideration there, and the crowding of the environment. So we can't really rely on ports and far field concepts to describe what is happening in the near field. And that is where an understanding of this is important. I said impact on MIMO systems, and I'll show an example in there. And we basically show that in designing a MIMO system, you have to go beyond the circuit parameters and the S21 to characterize systems and so on. Let me just take this example here where we could run into trouble. If you have a source, and that source, you know, the device here that we want to model or something is in the near field of the source. So we really need to know the source, the near field, to describe the interaction process. Okay? The other scenario, even if you have a far field coming at your device. So the source in the far field, and then there is a scatterer close by. That scatterer scattered in the field in the device, and the scattering is in the near field. So you really need to model this not based on a plane wave expansion or something, but you need to know the near field. So I'll start by talking about the near field theory here. And these are the concepts I'm going to talk about. And here's some critical question that I pointed to in the beginning. Is, do we know how a given antenna radiates? Well, antennas have been around for so long. But really how the energy leaves the antenna and gone, you would be astonished to see in the big textbooks that there isn't really a full explanation of this fundamental thing. And the question of electromagnetic energy. Well, let me take this is when devices get crowded, as I say, and all of these applications, near field, communications, everything coming towards us. And this is why knowing the structure of near field is important. Well, in textbooks, well, you do for some approximations where it's the near field and far field, and all of these are basically assumptions. But we don't know really what's happening in the near field, far field. Let's take the most simplest antenna we have, which is the Hertzian dipole, elemental dipole. In any textbook, you see these equations here. The field, and you do the curl, and so on, and you get this. But you notice we have H, 1 over R, 1 over R squared, E. So we talk about far field, immediate field. Well, these are all heuristic. These are all assumptions. But you notice here the 1 over R series. And there is really no such description for any other antenna. So this is basically where we started. And well, any far field is known, but this is so the. I'll walk you quickly through the development here, theoretical development, and highlight some of it, but I'm not going to get into details. So what we're doing here, we're going back to the old development electromagnetics, and we use something called Weyl expansion. You notice the dipole was 1 over r, so we're using here an infinite r series, summation, and we use spectral domain. Spectral domain is basically Fourier series transformation, or so this is basically the cornerstones of the development we have. So we actually take any antenna, expand the field around it, an infinite summation that you're going to see now, use multi-Weyl expansion, which is an integral form, use multi-pole expansion, which has been around for many years, and you can find it in any books. In old books of electromagnetic theory, and combine the three of them. There is a bit of an organic relationship between three of them. And this is a Weyl expansion. And you can see here that we're going with an expansion over infinite summation for the E and the H. And this was a paper written in 56, and strangely enough, it has not been, or it was not noticed by the community at that time. Multipole expansion, which is basically an eigenfunction expansion, and this is in the book, in the classical book in Jackson's classical electromagnetic theory. That's more of a advanced book there that graduate courses in electromagnetics use it, and then the Weyl expansion, which is basically an integral form here in the special, and these are the wave numbers and so on. The normal theory that you see. So this is basically, you can see that the antenna would be right in the middle there, and these are the regions around the antenna. So any antenna, this expansion would apply to it, and you can see here the summation R0 at the far field zone, R infinity is you can come close to the antenna, so you basically surround any antenna with a sphere as close to the antenna as possible. Well, using this, and after quite a bit of math and so on, you actually get expressions for the fields around. You get expressions for the energy in the electric and magnetic fields. You get quite a bit of information from that. And these information are applicable for any antenna. So this is actually a new development, and you can examine the energy, you examine them in mutual interaction. We actually find that the field, in the near field, there is propagating and non-propagating mode, and they kind of interact back and forth. So there is actually evanescent fields around, and they cover all the spectrum and so on. We're using a spectral representation, so you can find all the wave numbers and find the evanescent field and so on. The multipole expansion, I'm just showing it here. And this basically, if I go back, the coefficients that we talk here about AN and PN, this is how they defined in terms of the harmonics. As I say, we go back to the original book there. You get complete expressions for the analytical energy, and if somebody wants to use this expansion, as I said, there are a couple of papers written on that. So if you want to use this expansion, you actually start with the far field and you follow these steps here. And these steps for any particular antenna, and you can actually find the information about the near field of the antenna. As I said, using these expressions, we actually can answer some of the questions about the energy around the antenna. And as a matter of fact, in the next APS in Vancouver next year, we're going to have a session specially dedicated to that with researchers debating these questions that have been around for a while about energy. I mentioned earlier the concept of localized energy. Depending on the antenna and so on, the energy cannot be, it kind of can be localized in a region around the antenna in certain directions and so on, and you can find that. And we're coming this concept radial localized energy. You're going to take a radial direction from the antenna and find the energy across it. And that actually might lead to some new experiments, because you can actually come close to the antenna and use a small probe, and the resonance of that probe would, depending on the spatial resonance here, would tell you what kind of a field around the antenna exists and so on. And so it actually it could lead to new development and new work on antenna that is new. Now, I'm going to go to the second part of it. Having considered the field around one antenna, then you put two antennas together. So actually, the near field theory, looking at what's happening, gave us a bit of a thorough look at what could happen on antenna itself, relation of the field around the antenna to the current on the antenna. And this is why we came up with the concept of antenna current screen function, which I'll explain in a second. And basically, that combining these two together give us a way of doing some analysis that you'll see in a second, giving an example here. So you can actually use, like so far we use conventional methods of wave analysis. So the new approach, you combine the measurement with the theory, and you can actually do quite a bit of things. And one advantage here is actually once you do that, you don't have to keep solving Maxwell's equation every time you do the problem. And I'll explain in a second how is that. So let us look at the first approach, which is the dipole model here. What's the dipole model? This is a bit of a simplified model. And it helps us explain the theory and so, but it's not thorough enough. But what is the idea there is you actually take an antenna, measure the field around the antenna or know it somehow, then develop a model of a number of infinitesimal dipoles. The variation here, the moments of the dipoles and their orientation and the phase between them, you can find from an optimization scheme. And this model will actually represent the field. It can produce the near field. Again, you use an optimization algorithm. And then from this model, you can actually characterize the antenna and characterize everything that is there and know the near field and so on. And this is basically the procedure here. So the basic idea is spelled here. You know the field. You can actually find the number of dipoles, their orientation, and so on. And basically leave the antenna alone and do the analysis using these dipoles. So we use this model to do some of these examples here, like apply it to study mutual coupling, apply it to do near field synthesis, and I'll show an example here. And you can actually use it to look at nanostructures, paired object target detection, and so on. These are some of the papers that just appeared that we have looking at this here. So here is an example of the basic idea here is it possible to design an antenna that will give you a certain far field? So if you have a certain far field, focus far field, and so on, how would you design your antenna to produce that field? And following this procedure, I'll just explain to you the results here. So what you have is, if you look at two cross dipoles like this, and they're producing this far field here. So can I, applying this algorithm and using the field, either the far near, we came that the idea that these, if you look at these 5 dipoles here, their location and your orientation, their properties, will actually produce the same field like this here. Okay? So what is that telling us is you can actually use this infinitesimal dipole model to synthesize any near field or any antenna distribution. So the next thing we're doing now is you'll hear the talk about small antennas and so on. So the question is, can you optimize these things to actually occupy a less space, and then you have a smaller size antenna? So we talk about the small antennas and so on. Can you do that to have the field, the far field there? Now, come to the concept of antenna current stream function. Well, what is that? Go back to the basics here. And I don't know how many of you heard the new generation, at least heard about Shelkonov. But I see some people here smiling to see the name mentioned again at this time. But actually, Shelkonov tried to do some transfer functions or transfer admittance for antenna. At that time, there was no numerical method. The method of moments were known and so on. So he took an antenna, cut it into small pieces, and tried to do a circuit model to each antenna. And using this circuit model, he tried to construct a model for the whole antenna and so on. There were some questions here. This concept was basically a circuit model, and that didn't really go too far, and it was not, there wasn't a follow-up on it. So this is basically the forerunner of what we're calling the antenna Green's function. And there are some problems with his model, as I explained originally. So if you look at here, we start again with the basics. And we actually use Shelkonov concept of superposition antenna system. What we do it in a certain way. And as I said, there is quite a bit of math behind that. I'm not going to go into the details here, but I'll explain in a bit of a peculiar way the concept. And again, we engineers like to love to do work with systems. So if you're looking at a transfer function of a system, if you look at the spectral domain, temporal domain, we use this in circuits. So H is the transfer function of the system. So basically, space. The output is also a function in space, but the input is a field incident in the antenna. The output is the current that's existing on the antenna. So this is basically a totally new concept. And if you do that, then you have what we call the antenna current Green function. So it's basically a spectral domain. So as I said, this is a bit of a different concept. And basically, how you determine the antenna current Green function, there are various ways to do it. You can do it from measurements. You can actually do it using numerical methods with some development and so on. But you can see that the excitation here is just like in system delta function, special delta function. I'm not going into details of it here, but it's a bit analytical. But you actually have the current that's in the antenna. Once you have a transfer function for the antenna, then you don't have to redo the analysis every time. So use it just like you use it in system analysis. And here we have a method to propose to how you can even do measurements and determine it. And just for those of us who are familiar with the Green functions, you heard the term Green functions before. So here I'm trying to provide a comparison between the antenna current Green function, the new concept that we're talking about, and the classical Green functions in EM theory. So on the conventional Green function here, you have a current. This is how we start. We have a current on the antenna, so we find the Green function. And this is the expression here. So this is the Green function for the classical situation. The antenna current Green function is a bit different. You actually have the incident field on the antenna, specified incident field, and that could be a near field, and this is where comes the near field concept in there. And the response here, the current is the antenna current Green function. So similarities both involve convolutional integral, as you can see here. Both are assuming superposition. Both are dyadic, but the difference, the antenna current Green function, the conventional Green function is known with e to the ikr over r It's known in a closed form. The antenna current gain function is not non-closed form, so you have to work your way around to get it. And it is a bit more complicated, but it is there. We used this concept of the antenna current gain function in some situations, and we have it now open. I think there are already some people that are starting to use that concept. And we used it for dealing with arrays, near field problems, and MIMO systems. So I'll just give you an example, a recent example of what we use it in MIMO systems. What's a MIMO system? Well, you have multiple input, multiple output here, and the parameters of any MIMO system is you're worrying about the channel capacity, you're worrying about the torque, and the important thing is the cross-correlation coefficient. So the cross-correlation coefficients, there are expressions to determine it, and one of them is basically based on the far field expression. The second one is based on the S parameters. The one here is computationally difficult to evaluate, and you can actually do quite a bit of measurements. The one in circuit parameters, there are some questions about it. Again, you can't use circuit parameters to model a field effect. And in MIMO system, when you bring too many antennas together and trying to optimize the space and so on, relating things to the currents on the antenna would be a more accurate situation. So using the concepts that were developed earlier in antenna current gain function, we actually came up with a new expression, correlation expression, that is actually related to the currents on the antenna. So now you can control the currents on the antenna to optimize your correlation and so on. So with this expression, this is actually is going to appear in a couple of months. With this, you can directly optimize the surface current to minimize the cross-correlation coefficient. And here is an example. We're using a simple example here, 3-wire antennas. So the question is, can you optimize the currents on these 3-wire antennas to have an optimum correlation? And optimum correlation, this means the fields of each antenna will be distinct, and you can decide about it. And using this procedure that we've done, you can actually see these are the results of the current. So these are the currents, and these are close to, I think, half a wave dipoles and so on. So you can see that the current on the 3 antennas resembles what would you expect on a half wave or quarter wave dipole, whatever. There is a bit of a difference in the current. But the important thing is the variation in the phase. So you can actually control the phase of the current and quite a bit, and the amplitude to actually get the optimum correlation coefficient. Advantage of the antenna current gain function in terms of analysis. There are many advantages there, and as you can see here, it led us to quite a bit of new information about the fields and so on. And the one in red here, which we expect would have some implication, is basically if you combine the antenna current gain function with whatever existing in numerical methods, it would actually simplify the analysis and simplify the analysis quite a bit, because you don't have to repeatedly solve a Maxwell's equation if you want to do the simulation. And it is these new applications here, near field communication. Well, we do near field communications, but we don't understand the near field. So here is a way to get a more inside the same thing with the near field matching and so on. As I said, this is work lasts over 3 or 4 or 5 years. It's still early, and there's quite a bit of things developed. Now we look at, you can't go without touching on metamaterials here. And as I said, metamaterials, people talk about it in terms of temporal variation and dispersion curves and so on. Well, what we're looking at here is actually metamaterials that could respond to spatial variation. I just mentioned that we had a question about, we looked at the energy and we talk about localized energy around this. So the question is, if you know how your energy is spread around the antenna, can you design material to work around that? Because you know what would be hitting the material. The other question of energy, harvesting, whatever. Well, you have a full picture of what happens around the antenna here. Here, anybody who wants to look at these things, there are some tools that would help. It's not so. In conclusion, as I tried to explain, we have looked back at the fundamentals, came up with some descriptions of the fields that we think describe the near field around the antenna, describe the interaction. We have new models of the antennas that are basically a way of characterizing antenna as a system. This is a bit of a new concept, which is antenna Carl-Green function. We have applied it in many situations, applied it to study mutual coupling. And we hope that basically the theory and the development here will lead to more, or a new look at how we do things in electromagnetics. This is a list of some of the papers, if anybody interested. And there is actually, if you look at reference 12 here, we're working on a book that's gonna add all of these results for next. It's going to be published next year, and also there's going to be short course at UCAB and the APS next year. So I'll stop here and try to take some of your questions.